Hello everyone and welcome back to the next module in Operation Research. In this particular module, we are going to have a look at the second part of Simplex method, what is called as duality theory. The duality theory in linear programming states that every LP problem has another LP problem related to it and thus it can be derived from it. What it means is associated with every linear programming problem, listen carefully, associated with every linear programming problem, there exists another LP problem, that is another linear programming problem, which is based on the same data, right? Which is based on the same data having the same solution. Now, if this happens, the original linear programming problem is called as primal, while the derived one is actually called as dual. So we have something called as primal linear problem and dual linear problem. Now, if optimal solution to one is known, then optimal solution of another one is readily available. So we have primal problem and we have its duplicate version, what is called as dual problem. So if we make an attempt to implement the simplex procedure and try to solve one of those problems, one of the existing LPP, that is either primal or dual, then we don't need to basically spend time in solving. We will readily get the optimal solution for the other one. Means I have primal form, I solve it, I get optimal solution. And then I will have or I will derive the dual of it, and without solving I will have the optimal solution with me. Okay, so as and when we proceed, you will understand this particular concept of readily available optimal solution. In some cases, considerable amount of computing time can be saved by solving the dual. A point to be kept note is the advantage of dual simplex method is it can avoid the artificial variables. Right now, that is the major advantage of dual simplex method. What? You can avoid the artificial variables introduced in the constraints along with the surplus variables, as all greater or equal to constraints are converted into less than or equal to type. So that is the reason where you can always avoid artificial variables going into the first table of your simplex table. Now, some of the important characteristics of duality. Dual of dual is primal. If either the primal or dual problem has a solution, then the other one also has a solution and their optimum values are equal, right? So what does the second point mean? Their optimum values are equal. Of course, there might be a small change in the values of the decision variable, but it will not affect the optimal solution. The third characteristic is if any of the two problems has infeasible solution, then the value of the objective function of the other is unbounded. Fourth, the value of the objective function for any feasible solution of the primal is less than the value of the objective function for any feasible solution of the dual. Let us move into the last two characteristics. The fifth one is if either the primal or dual has an unbounded solution, then the solution to the other problem is infeasible. And the last, if the primal has a feasible solution but the dual does not have, then the primal will not have a finite optimal solution and vice versa. Let us look into the advantages of duality. First, it yields a number of powerful theorems. Second, computational procedure can be considerably reduced by converting it into dual if the primal problem contains a large number of rows and small number of columns. Third, solution of the dual checks the accuracy of the primal solution for computational errors. Fourth, it gives additional information as to how the optimum solution changes as a result of the changes in the coefficients and the formulation of the problem. Particularly, it is termed as post-optimality or sensitivity analysis. The fifth advantage, it indicates that fairly close relationships exists between linear programming duality. Right? I'm sorry for the typo. Exists between linear programming duality. The last advantage, economic interpretation of the dual helps the management in making future decisions. Now, before we make an attempt to solve the problems which involves or which is revolved around duality, let us see the applications of duality. The first one, in the areas like economics, it is highly helpful in obtaining future decision in the activities being programmed. Second, in physics, it is used in parallel circuit and series circuit theory. Third, in game theory, dual is employed by column player who wishes to minimize his maximum loss while his opponent, that is the row player, applies the primal to maximize his minimum gains. But however, if one problem is solved, the solution for other also can be obtained from the simplex table. The fourth application, duality can be very much useful in areas of sensitivity analysis. And the last one is perhaps the most famous application of duality has been in max-flow min-cut theorem or max-flow min-cut problems, wherein the theorem states formally that the optimal solution for primal integer LP, which is to find the maximum flow, is actually equal to the same optimal solution for the dual, which is basically to find a minimum cut. So that is called as max flow min cut theorem. Now, general rules for converting the primal into dual. So these are the rules, right? So what we do is we understand these rules by solving one or two problems, and then I'll give you one or two problems for you to solve. Okay. So let us make an attempt to solve this. Obtain the dual of the following LP problem. Right. So from Microsoft PowerPoint, let me take you back to Microsoft Word. So here it is. You have in front of you the rules for converting the primal into dual. Right. So these are the 5 steps. And then let us proceed with solving the problem. Now this is the problem. What it says, obtain the dual of the following LP problem. So you have the objective function as maximization. So this is your objective function subject to 2 constraints wherein it is actually equality constraints. So total number of constraints are 2, which are actually equality constraints, right? Now let us see how do we proceed with obtaining the dual. So what the first step says is you need to have the problem statement in the standard primal form. So what is standard primal form? If the objective function is maximization, then the constraints should be of less than or equal to type, right? The constraints should be of less than or equal to type. So the step it says is, right, if the constraints has equality sign, then it is replaced by 2 constraints involving the inequalities going in the opposite directions, right? So what you are trying to do here is you have an objective function with equality constraints. So the primal form will go into inequality constraints. So that's what this step 4 says, that if the constraint has equality sign, then it should be replaced by 2 constraints. Watch out carefully. Each of this will be replaced by 2 constraints. So this one will be replaced by 2 and this one will be replaced by 2. So totally we will have 4 constraints for this objective function. Now when this is going to be reduced to 2 inequality constraints, right, the first of this will belong to less than or equal to category and the second one will belong to greater or equal to category, right? So first one is less than or equal to, second one is greater or equal to. That is what it says, that involving the equalities going in opposite directions simultaneously. Opposite directions means one less than or equal to and the other one is greater than or equal to. You have a look at this. This is what it is, less than or equal to and greater than or equal to. So similarly what we do is we will convert this into 2 and then we say the first constraint gets converted into two constraints. Watch out carefully. The first one gets converted into two constraints. The first one is less than or equal to, and the second one is greater than or equal to. Similarly, what happens? This one, the second constraint of the original problem, which has got equal to, this also gets divided into two constraints, one with less than or equal to, and the other one is with greater than or equal to. So this is my second constraint, right? This is my second constraint, less than or equal to 4 and greater than or equal to 4. Okay, now what happens when these two constraints, the one becomes less than or equal to and the other becomes greater than or equal to, this one also becomes less than or equal to and greater than or equal to, what you need to do is you need to actually bring it to the primal form. Okay, you need to actually bring it to the primal form. So this is the general rule for converting the primal into dual, right? So we will understand these steps as and when we proceed. Just spend some time in going through the steps. Make an attempt to understand. Of course, it will be more clear when we make an attempt to solve the problems. Okay, so let us proceed in solving the problem. The first problem is there in front of you. It says obtain the dual of the following LP problem. So I have the objective function as maximization and I have two constraints, but both the constraints are of equal to sign, right? So what the first step says is actually you should convert the objective function into standard primal form. What is standard primal form? If it is of maximization type, if the objective function is of maximization type, then the constraint should be of less than or equal to sign. Okay, so we have objective function as maximization, and hence this constraints should be of less than or equal to, it should be of less than or equal to constraint, right? Now what is the step it says is if the constraint has equality sign, then it should be replaced by two constraints involving the inequalities going in opposite directions. Means what? If you have something like this equal to 4, then it will be replaced by two opposite inequalities. Which are those two opposite inequalities? Less than and greater than. So this x1 plus 2x2 equal to 4 becomes x1 plus 2x2 less than or equal to 4 and x1 plus 2x2 greater than or equal to 4, right? So this is what you mean by saying that inequalities going in opposite directions simultaneously. Okay, and further what happens with this constraint which involves greater or equal to is, since the objective function is of maximization type, this constraint will be converted to less than or equal to inequality, right? And hence what happens, we we multiply, as you know, the entire constraint by minus 1, and hence this greater or equal to becomes minus x1 minus 2x2 less than or equal to minus 4. Okay, so let us see how it is with respect to our problem. So I have the first constraint 4x1 plus 3x2 plus x3 equal to 6. So since it is of equal to category, we will have two constraints derived out of it. These are the two constraints, right? One is with less than or equal to and the other one is with greater or equal to, right? Now since objective function is of maximization, I will convert this constraint which is greater or equal to into less than or equal to by multiplying with minus 1, and hence what happens, this greater or equal to will become like this with respect to less than or equal to. This we do because the objective function is of maximization type, and the first step in duality is we should get the original primal form, right? So when we proceed next to the second constraint, this is our second constraint with equal to. Again, two inequality constraint gets derived out of it, same as usual, one less than or equal to and another one is greater than or equal to. These are those two inequality constraints. Less than or equal to you can see here, and another one is greater or equal to you can see here. Now further, this greater or equal to inequality constraint will be again multiplied by -1 because the objective function is of maximization. And once we multiply it by -1, this is what we get actually, right? So I have my original objective function. This constraint got separated or got divided into two sub constraints, and this constraint also got divided into two constraints. So as a matter of fact, what I have is I have my objective function followed by four constraints, right? So let us see what are those four constraints, which I will say the final primal form will be like this. So this is my objective function subject to, watch out carefully, these are my four constraints. Now when you look carefully, these four constraints, all the four constraints are less than or equal to type, right? The reason is the objective function is maximization. Got the point, right? Since objective function is of maximization, my entire constraints are less than or equal to. So once I have this, I say that this is my final primal form. So for this particular final primal form, you have to find out the dual, right? So that is what it says, right? Obtain the dual of the following LP problem. So it is not that you directly go for dual. This is the first step where you have to ensure the given LP problem should be in primal form, right? Just check whether it is in primal form. If not, you have to convert it into primal form. And that is what we have done in all these steps. Okay, now how do we convert the final primal form into dual, right? So be careful, it's very interesting. Let us go step by step and understand slowly. The first step, okay? Now, when we say that we are going to convert this primal into dual, again, in dual, please understand, dual is nothing but another version of LPP. It's a duplicate version, I can say, of LPP. Means what? The dual will also have objective function. The dual will also have constraints. Got the point, right? So the way how you see on your screen, the primal has got an objective function and constraints. Similarly, the dual will also have objective function and the constraints. So what we are going to do is we are going to find out what will be that objective function, how it looks, and what are the constraints and how it looks in dual. So the first step is in primal objective function, or in primal, if the objective function is maximization, it becomes minimization in dual, right? So this maximize z, I will make it as minimize z. Okay, so this is the first step. Please understand, the objective function gets swapped in primal and dual, right? So if it is maximization in primal, it becomes minimization in dual and vice versa, right? Now the next step is this: the number of constraints in primal becomes the number of decision variables in dual. Got it? The number of constraints in primal becomes number of decision variables in dual. Now let us look at how many constraints you have. You have 1, 2, 3 and 4, right? So the number of constraints, here you have 4 constraints, and hence what is the second step is the number of constraints in primal becomes the number of decision variables in dual. So 4 constraints, I will call the decision variables as W1, W2, W3 and W4. Even though some of them they call the decision variables as Y1, Y2, Y3, Y4. I mean, it does not matter. So the 4 constraints becomes 4 decision variables of dual. I call it as W1, W2, W3 and W4, right? Now what happens? The third step, the right hand side of the constraints in primal, okay, the right hand side of the constraints in primal becomes coefficient of the objective function in dual. So be careful, the right hand side of constraints in primal. Okay, so what are the right hand side? These are the right hand side of the constraints. This 6, -6, 4 and minus 4, right? So these are the right hand side of the constraints in primal. What happens to those right hand side? They become coefficients of the objective function in dual, right? Now watch out. In the previous step we said 4 constraints becomes 4 decision variables, and for those 4 decision variables we should have the coefficients. That coefficient is nothing but the right hand side of this constraint, and hence in my step 3 I will get the RHS of constraints in primal, which becomes the coefficient as this. So my objective function is minimize z is equal to 6w1 minus 6w2 plus 4w3 minus 4w4. Right? Now let us go ahead in building the constraints for this objective function, which is now minimization. The step 4 in primal. Okay, so go back to your primal and find out this. The coefficient of the first decision variable in all the constraints, okay, becomes the coefficient of different decision variables in the first constraint of dual, right? So I mean, at first stretch slightly difficult to understand, right? Let us go back again. The coefficient of the first decision variable, okay? So let me go back to the primal and tell you that, see here, the coefficient of the first decision variable in all the constraints, right? So this is the coefficient of the first decision variable in first constraint. So this is 4. This is the coefficient of the first decision variable in the second constraint. It is minus 4. Similarly, this is 1. This is minus 1. Got it? So 4 minus 4, 1 minus 1. This is the meaning of that. What happens to them? It becomes the coefficient of different decision variables in the first constraint of dual. So the way we have extracted the coefficients of the first variables of all constraints from primal, they become the coefficient of different decision variables in the first constraint, right? So it becomes like this: 4w1 minus 4w2 plus w3 minus w4, correct? Now the next step, in primal, the coefficient of the decision variables becomes the right hand side of the constraints in dual, right? In primal, the coefficient of the decision variables becomes the right hand side of constraints in dual. Let us look at it. What are the coefficients of the decision variables? 2, 3 and x, that is 1. So the coefficient of the decision variables is in objective function is 2, 3 and 1. They become the right hand side of the constraints in dual. Right? So the first coefficient of the the coefficient of the first decision variable in primal was 2, so it becomes the right hand side of the first constraint. So the first constraint of dual is this one, and hence what happens, my final dual looks like this. So this is my final dual. The maximization of primal became minimization in dual, right? And since it is minimization, my entire constraints are inequality constraints are greater than or equal to, right? So this is how you land up obtaining the dual of the existing primal. Let us take one more example. Here I have obtain the dual of the following problem, right? So again, my objective function is minimization, right? And let me check whether I have this given problem in standard primal form. And when I observe this greater or equal to and this equal to, so it is not in standard primal form. So I will first write this particular LPP in standard primal form. So I'll have this minimization equal to, no doubt about it, right? Now what happens is I have the first constraint greater or equal to, so no problem, there's no I don't need to change this. But look at my second constraint. My second constraint is having less than or equal to as inequality constraint. So what I do is I will change that into greater than or equal to, right? So how do I do it? I'll multiply it by minus 1. So I'll get minus 2x1 minus x2 minus 6x3 greater or equal to minus 6. So that is how my second constraint looks like. Now look at the original third one. This is inequality, correct? As we have seen earlier, inequality has to be uh, actually it gets converted into two. One less than or equal to and another one is greater than or equal to. So this is what it is. This is greater than or equal to and this is less than or equal to. Both getting derived for this particular constraint, which is equality. And further what happens, this less than or equal to, right? Because it is minimization, I have to convert this less than or equal to constraint into greater than or equal to by multiplying by -1. Okay, so keeping all these things in mind, right? So what is it? This is my objective function. This is my first constraint. Okay, then this is my second constraint. This is my third constraint and this is my fourth constraint, right? So keeping all these things in mind, this is how my standard primal form looks like. Okay, so this is what is my standard primal form. So when you closely observe, I have minimization with greater or equal to. All my constraints are greater than or equal to. Okay, now to obtain dual, keep same points in mind and then let us proceed, right? So the minimization becomes maximization in dual, correct? Then, okay, so it is maximization 2w1 minus 6w2 minus 4w3 plus 4w4. How is it? The right hand side of the constraints of primal, correct? So this is the primal. The right hand side 2 minus 6 minus 4 4, they become the coefficient of the decision variables in dual. So I have 2 here, you see -6, then you see -4 and you see 4. Okay, so this is my objective function in case of dual, right? Now let me proceed with respect to the constraints. Look at the coefficient of the decision variables. Here it is 1, then this is -2, this is -1 and this is 1. So 1 -2 -1 1. So this is what it is, 1, this is -2, this is -1 and this is 1, right? So this is my first constraint of dual, right? Then all the constraints in dual will be of less than or equal to category because it is maximization, right? Now what is this 0? How did you get it actually? Now this is, look at your standard primal form. Now in standard primal form, you do not have a variable x1. Since you do not have variable x1, the coefficient of that will be 0 and hence the right hand side of the first constraint in duality, it becomes a 0. Okay. Now let me look at the second constraint. Look at this. Primal constraints. The coefficient of this is 1. The coefficient of this is 1. I'm sorry, -1. This is 1. This is -1. So I have 1, -1, 1, -1. Have a look at this. So I have 1w1 minus 1w2 plus 1w3 minus 1w4. And then the coefficient of the second decision variable in objective function, that is 2 here, becomes the right hand side of the constraint, right hand side of the second constraint. Okay, and similarly my third constraint of dual will be like this, and hence I say that the dual of this particular primal is nothing but this one. Okay, and of course I cannot ignore this. I'll have w1, w2, w3, w4 greater than or equal to 0. Okay, so this is how you basically land up converting the primal into dual, right? So my sincere request is kindly go through these take down these problems, correct? So take down this problem, write dual for the following LPP, okay? And once you take down this problem, right, sincerely go through the steps once again and try to find the dual of this, right? And once you get the dual of this, right, just compare the dual that you have got with what the answer I have written. Okay, so that will just boost up your confidence actually, right? So similarly, take one more problem. Now here I have objective function as maximization with these constraints and try to get the dual of this particular problem, right? And once you get the dual of this, please cross verify or please check the dual is this one. Okay, so the maximization became minimization, and just have a look at it. All my constraints are greater than or equal to. Okay, so even though I have just restricted here because of various other constraints into two problems, as I told you earlier and I have been telling, please take more and more problems from various sources and try to solve so that you will have more grip on the subject.